Dear learners, very good afternoon to all. We'll start our course on quantum electronics 2, and today I will discuss about the foundation of the quantum heterostructure. That will be the topics today. Now, before going to the course, let me briefly recall that in quantum electronics 1, we have covered the several numerical techniques like perturbation method, variational approximation, the WKB method, and so many numerical techniques, but which are not generally used today. And in that context, I have said that these techniques are now obsolete to 30-40 years before. So, in this course, we will really map our prerequisites, that means our foundation of our BSc level quantum electronics, where we start with our Schrodinger equation and then move to our basic semiconductor physics, what we have learned. Along with that, we will map our concept of the material science, and that amalgamation will lead to the potential applications of the quantum electronics. Now, let me go a little bit in a deeper way. Just start with a elementary level quantum mechanics problem which we have learned in our undergraduate course. That is a infinite quantum well problem, that is a particle in a box problem. What we learned in particle in a box problem, that we have a very deep well. I will come to the concept of actual quantum well a little bit later on, but let me go to that level. We have a very deep well where the bottom level has potential V equals to 0 and top level has potential V equals to infinite. And we beautifully utilize the Schrodinger's equation and we get the energy eigenvalues, eigenfunctions, and we said, okay, we have really applied and get some results. Look, have we ever thought that a well is possible with a potential height infinite? Anything infinite is possible in this realistic world? The answer will be not. But however, due to some unknown reasons, at that time, we never thought that it is really possible, whether what we are solving, is it really possible or not? Never. At that time, we are very happy that we have solved, we have applied the Schrodinger's equation. Again, what we thought, that it's a potential well who has a beautiful step function. Now, if you recall your foundation of signal and system concept, step function is a function where at a particular value of x-axis, two different values of y-axis are possible. Please think. At a particular value of x-axis, two different values of y-axis are possible. Is it really possible? The answer will be no. So we have dig to great mistakes and we solved the Schrodinger and we have got marks awarded. But once we have to go into the research, once we have to go to the semiconductor industry, why I am talking about semiconductor industry? It's the biggest industry now. Forget about India, but it is the biggest industry in the world. They won't absurd, call these concepts absurd. Your concept of step function and your concept of infinite potential well, like those things. So what we have to do? We have to do something which will be realistic. That means the mathematics, what we have learned, the Schrodinger equation, that should be applied to the physics of semiconductor devices. Up to that, we have isolated them, but we really have to amalgamate it along with the material science. Now look, till now we have generally neglected this material science part. If you again please recall that particle in a box problem. Have you ever thought that particle in a box problem deals with some sort of material parameters? No. We have assumed free space effective mass. How a well is possible in free space? Never thought. We have assumed outside of the well there is nothing, air, free space. So how a well will be floating in a free space? Never thought. So again, actually the realistic physics, how a real quantum well will be formed. Actually the real quantum well formation will be discussed in our next day, lecture 2. But how a quantum well will be formed, that we never thought of when we have undergraduate level started our journey. Nonetheless, we have never thought about the material science. So silicon, gallium arsenide, if we have our known semiconductors, what will really happen? But when we are using a smartphone or laptop or something else, we know these are realistic devices. That means the semiconductors are realistic. This is not made in free space. So we have to consider all these realistic phenomena in our calculation. The question will now come that how we can really amalgamate this mathematics, material science, as well as physics of semiconductor devices, and this amalgamation will lead to the application which we are using in our day-to-day life. So that begins our journey to the quantum electronics too. Now the question will be, you may say that we know everything about Schrodinger equation till now. Okay, fine. So what will be the semiconductor devices, or what will be the physics of semiconductor device means? Obviously, if you open the textbook of any semiconductor device, it deals with the band structure. That's the chapter 0, we can say. So how we start with the band structure, how we really deal with the band structure, that will be our primary objective of investigation. So let's start with our journey from the concept of band structure, and in that context I will again recall a fact that we start with our journey with the class 12 or class 11, where we start Mendeleev's periodic table. You will say, why the chemistry course? No, not chemistry. It deals with our two very fundamental parameters on which everything is based. What are the fundamental parameters? Number one is called work function, and number two will be called electron affinity. So let me start our journey with these two very crucial parameters. So refresh your knowledge. Let's start. Now again I will trace an existing concept that in our earlier days, when our school days or in undergraduate college days, we know that Fermi is a foundation for any band structure. No, sorry. If you again recall your school level, you may aware that there is a course or chapter on Bohr's atomic principle. And what Bohr's atomic principle deals with, we are mostly familiar with a known calculation of hydrogen, or more precisely protium, that is 1H1. And what it gives you? It gives the energy values of electron, and that is minus 13.59 electron volt, or minus 13.6, somebody approximated it. But why minus? Because at that time we say that the highest value of energy is 0 volt, or 0 electron volt, sorry to say. And 0 electron volt, it is called vacuum level. And that is our reference level, and we are measuring everything with respect to that reference level. So again, I will start with the concept of the Bohr's energy diagram, where our reference level is obviously the vacuum level. And once we will deal with the vacuum level, every measurement with respect to that one. Now, take a semiconductor. There is conduction band, valence band, and take it as a non-degenerate semiconductor, so Fermi is in the forbidden region. Now, electron affinity is the amount of energy required to liberate it from conduction band to vacuum level. Please remind, electron affinity is the amount of energy required to liberate an electron from conduction band to vacuum level. Whereas work function is the amount of energy required to liberate an electron from Fermi level to vacuum level. The difference comes, both are liberation of electron, both the cases it will reach to vacuum, that means vacuum level, but in one case the journey restricts between conduction and vacuum. In another case, it is restricted between Fermi and vacuum. So that's the distinguishing factor, I may say. Now recall in your school level another chapter of photoelectric effect. What is that? You know the work function concept, introduced Einstein's equation, like those things. At that time, we deal everything like work function. What is the problem? No, there is no problem. Please think. In photoelectric effect, we deal with the metal. We deal with the metal, right? Yes. So while we deal with the metal, please know that metal conduction band and Fermi level are same. So the work function and electron affinity are naturally equal. So at that time, we never thought about distinguishing between work function and electron affinity. But once you come to the case of insulator or semiconductor, now the problem appears, because your work function and electron affinity are not same as the Fermi and the conduction band are not same. They are parallel, but they are different. So now the distinguishing factor for a semiconductor, for a non-degenerate semiconductor, work function greater than electron affinity, and for a degenerate semiconductor, say n-type, for a degenerate n-type, work function less than electron affinity. Now the concept I think clear. So with this basic concept of work function and electron affinity, we go to the heterostructure and homostructure. Let's go to this case. Now I start with the Homo junction, say PN junction. Now first let me distinguish between homo and hetero. Point number one, both are junction. Make it very clear, both are junction. Now remind, if in either side of the junction band gap of materials are different, then it will be heterostructure. But if band gap is same, that means same material, obviously. If you change material, then only band gap will be different. But if band gap remains same in either side of the junction, it will be Homo junction. So take about our known example of PN junction started from your earlier school level. P and N both are made by same semiconductor, silicon, gallium arsenide, whatever. So band gap remains same. Now how it happens? Now look. Since both are semiconductor of same semiconductor, that means equal band gap, then their electron affinity will be equal. But for p type, Fermi level is very close to valence band, and for n type, Fermi level is very close to conduction band. So what will happen? For equilibrium, if we have to align the Fermi level, then the band will bend both the conduction and valence, and they will bend in the form of same radius of curvature. That means if they have the same radius of curvature, means the vacuum level will also bend with the same radius of curvature. The question will be why? Because you have to make the electron affinity equal in p and n side. So if you bend conduction, then you are also bending the E equals to 0 level. That's why we consider Fermi level as reference level for Homo junction, and we made all our calculations with respect to the Fermi level. But again, please recall the college level concept of Schottky contact and ohmic contact. You replace one side by metal and forget about Fermi. You start with dealing with the vacuum. That is basically called Anderson's rule, which says that if you have to do with heterojunction, then you have to consider the alignment of vacuum levels. That's the primary thing. So if I move towards the heterojunction, which is the figure in the right side, look, with respect to the hypothetical vertical line, left and right side, there are two semiconductors, and band gap of both the semiconductors are different. So what we will get? If band gaps are different, but vacuum level is constant, then electron affinity Obviously, different materials means electron affinity will be different, but vacuum level is constant. Now comes to the case, compare the two diagrams. In the previous case, you are bending the vacuum level. In this case, you are making the constancy of vacuum level. And there is no requirement of Fermi because Fermi continuity is not at all required in our calculation. We will make calculations with respect to vacuum level. So that will be our starting point. So I think the difference between Homo junction and heterojunction is very clear to all. And look, if you have this difference of the electron affinity, I am starting from the reference line. If you have the difference of the electron affinity, then there will be difference of conduction band. That is called delta EC. Delta EC is known as conduction band discontinuity. I am repeating again, delta EC is known as conduction band discontinuity, and similarly the valence bands will also be discontinuous, and that is known as delta EV. Delta EV is called valence band discontinuity. If the question is given why both the discontinuity arises, simply because of the difference of the electron affinities of both the materials. So that will be our starting point. Once we know the delta EC and delta EV, let's go towards the classification of the heterostructure. Now look, there are three different types of the heterostructure. I will call them type 1, type 2 and type 3. Let me go into slightly more details. What is type 1, what is type 2 and what is type 3? In type 1, look at the figure very closely. I took two semiconductors of two colors, one is green, another is violet. The smaller band gap semiconductor, that means the violet one, is completely sandwiched or completely covered, better to say completely covered by the green semiconductor, that means the larger band gap semiconductor. I am repeating again, the smaller band gap semiconductor is completely covered by the larger band gap semiconductor. That means both delta EC and delta EV arises with different energy direction. Delta EC is measured from lower conduction to upper conduction, and delta EV is measured for lower valence to upper valence. That means, upper valence to lower valence. So it is downwards. So both are measured in different direction. This is also known as straddling. Now I am going to the type 2. Look here, lower band gap semiconductor is partially covered by upper band gap semiconductor. That means you will get again delta EC and delta EV, but there is a problem. You are getting them, but the measurement is in same direction, because lowered EC to upper EC and For the same semiconductor, now valence band goes more downwards. So you are not completely covered, but it is partially covered. If you shift it further downwards, the violet one, a situation may arise that there is no overlapping. That will be called type 3 or broken gap. So if their band gaps are shared, one is covered by another, it is straddling or type 1. If there is partial overlap, it is type 2 or staggered. If there is no overlap, it is type 3 or broken gap. I will come to the each of this case in more details with some real examples of the semiconductor. But till now I am dealing with the physics of semiconductor devices, yet to incorporate the concept of material science. So we have type 1, type 2 and type 3. Now, I am coming to type 1 in more details. Look at, I am taking gas and gas for a particular mole composition. Gallium arsenide has band gap 1.43, electron volt scale, everything. Gas for this mole composition has 1.8. Now gas has a electron affinity 4.05 and gas for this mole composition is 3.72. And I am also showing delta EC and delta EV. The question will be how these things are calculated. Let's look at the structure very clear. My blue semiconductor is gas and pink semiconductor is gas. Now, for gas, electron affinity is 4.05. For gas, it is 3.72. So what is the difference of the electron affinity? If I simply subtract, it will be 0.33. Fine, simple mathematics. Again comes to the band gap. Band gap of gas is 1.43 and gas, take here 1.8. So what is the difference? 0.37. Now again recall this picture. The difference of the electron affinity is nothing but difference of the conduction band. Simple. So if delta chi, that means difference of the electron affinity is 0.33 electron volt, then delta EC, that is difference of the conduction band, is also 0.33 electron volt. Very simple calculation from the structure. Now what is delta EG? If I subtract, it is 0.37. Now from the figure, delta EG, that is the difference of the band gap, is numerically equal to the delta EC, that is difference of the conduction band, plus delta EV, that is the difference of the valence band. So delta EG, that is 0.37, equals to delta EC 0.33 plus delta EV. So delta EV comes about 0.04. That calculation is shown in the next slide. That's the same calculation I am repeating. So delta EC for this case is much higher than delta EV. That calculation for gas is extremely important, because when we will go to the next lecture, lecture 2 for quantum well, we will take all the wells in the conduction band. Why? Because most of the example gives you delta EC much greater than delta EV. So confinement is better possible for electrons in the conduction band than the holes in the valence band, and that's the argument we will use later on. Next comes to the staggered. Staggered, I am dealing with indium phosphide and ilmium aluminum arsenide. Look, their band gaps are very close, 1.35 and 1.44. Naturally, if you slightly shift the lower band gap semiconductor, you can't completely cover. It's very simple. Two things of almost close thickness. So if you shift one downwards, naturally its valence band goes outwards. So delta EC and delta EV now look here. I am giving two brown arrows with the respect to the green horizontal lines, and that is staggered. So it has a realistic implication I will come to later on, but please think they are now partially, not completely covered. And if I go to the broken gap, take indium arsenide and gallium antimonide. Gallium antimonide is 0.73, indium arsenide is 0.36. Now they won't share. The conduction band level of indium arsenide is lower than the valence band level of gallium antimonide. So it is so much shifted that the joining of the conduction band and joining of the valence band gives a huge depth. Because there is no overlapping zone of their forbidden regions, that's why it is called broken gap. I am repeating again, since there is no overlapping zone of their forbidden regions, that's why it is called broken gap. So I am giving three examples of three heterostructures. These are classifications, type 1, type 2 and type 3. And you know this. Details, please remind. Now look, in all these examples what I have did, I have intentionally introduced material science in the physics of semiconductor device. So I have three parameters I have saved for going application: physics of semiconductor device, mathematics and material science. Already I have coupled both, two things. If you want to proceed further, you have to look about the mathematics. Now, why I will come to the mathematics? Because complexity of the analysis. Please think. Our first approximation, we generally deal with the effective mass. What is that? Suppose in a p-n junction, when an electron goes from semiconductor to wire, we assume its effective mass remains constant. But is it? No. We know that effective mass depends on the band structure. And it's different in conduction and valence, and is also different from point to point in the conduction band. So how the electron has the same effective mass in different materials? Sorry, that's the wrong concept. Once we have to go into the nano level, these very, very tiny things have to be taken into consideration that have a bigger impact. So effective mass approximation means we can't now approximate. We have to take effective mass is different in different materials. Second, I have already said the step potential. A step function means at a particular value of x-axis you have two different values of y-axis. How is it possible? Never. So the rectangular potential will recall your particle in a box problem. The rectangular potential will problem is never valid. Now when you have these problems, now look into your another concept or another tool that is called mathematics. What is that? We have to incorporate the boundary conditions. And these boundary conditions first published in 1966 by Ben Daniel and Duke. It's a Physical Review B paper. You can search in Google, probably it's freely available now. What they said? They said that the wave function in region 1 and region 2 means wave function or in semiconductor 1 and wave function in semiconductor 2, those are continuous. Now I am going to the wave aspect of the quantum mechanics. And we know they are first order derivative but not direct first order derivative. Please recall. They are normalized first order derivative. How normalized? Normalized with respect to zonal effective mass. That means d psi 1 dz divided by effective mass of region 1 equals to d psi 2 dz divided by effective mass of region 2. This is called normalized wave derivative of wave function normalized with respect to zonal effective mass. These two are the boundary conditions required to start the calculations of the quantum well. So now we have taken into consideration that effective mass is different in different materials. So the first approximation is eliminated. What is the second approximation? I have already mentioned. That is the step potential. Please look. We have shown three potential configuration. The first one is known to all, rectangular potential, forget about. If you compare a triangular potential and a rectangular potential, look what is the difference. As you move towards the inclined potential value, at each point your V value is changing. But if you go for the straight, that means the rectangular or square potential well, at any point of the barrier, the V value is V equals to V0. But I can't say for a triangular potential well. V equals to V0 at the corner. But if you approach towards V equals to 0, every point it is changing. That means at every point, if you take the cross section, if the vertical, if you chop around the vertical, every point you will get two different materials. Inside it is the well material, outside it is the barrier material. But if you look out the rectangular, barrier and well are beautifully separated. Now, why the question will be, why, sir, you are dealing with the triangular well? It's very simple. For MOSFET, the channel is triangular. It's never rectangular. So we have to deal with. Look out the parabolic, or I will come to the Gaussian later on. Again, it's a very complex. Even triangular has a very good linear function, but parabolic, that's a non-linear variation of the barrier material. So complexity of the potential structure now takes place. Nature gives us complexity. So once we have this complexity, we can't simply apply those our well-known Schrodinger equation in a very easily analytical method. So analytical method will not take shape. Now look out the last two structures. Once we mixing barrier and well materials from a vertical angle, we incorporate material science. We tilted the band structure, we incorporate physics of semiconductor device, and we are thinking about solution of the problem. We incorporate mathematics. So once these three are combined, our analytical techniques will no longer be applicable. So what are the techniques will be applicable? I am listing top 6. Transfer matrix technique TMT, propagation matrix method PMM, perturbation WKB, variational, and FEM and FDTD. Now, last two are extremely crucial, but in our course we don't have a legacy to go into that FEM and FDTD. But at least for a hands-on calculation format, we can use TMT and PMM. That calculation is easy. Once we go to the quantum structure, we can really fit in these two things and we can show how these things are possible. So Among these 6, we will took top 2 for our calculation purpose, and we will proceed in this manner a little slow step by step from the next class onwards. And so what will be our inference? We are very close to this class. That for realistic quantum confined structure, please look out the italic words, the realistic quantum confined structure, application of boundary condition, mathematics, realistic quantum structure means the combination of physics and material science. You require appropriate numerical techniques, mathematics. So what are those realistic quantum confined structure where we really incorporate this mathematics? These are the 3. Well, where, and dot. Quantum well, quantum where, quantum dot. So from the next class onwards, we start with these 3. We start to proceed, and now we will incorporate our mathematics. We choose appropriate numerical techniques, and we will try to solve by hand, at least in basic principle, how a realistic quantum structure can be solved. Till then, thank you all. We'll see you in the next class.